Hey there, this is Evan with EB3D Printing. In today's video, we're going to be tuning Input Shaper, also known as resonance compensation, on the Ender3v2. Input shaping is used to help reduce ringing, echoing, ghosting, whichever you'd like to call it. Ringing occurs due to the rapid movement changes of the printer during the 3D printing process. Input shaping reduces ringing through an open loop control. Essentially, this sends signals to the stepper motors on the printer, mainly X and Y, that cancel out the stepper motor's own vibrations. Input shaping is tuned one of two ways. The first, the manual method, is where you print a tuning tower, you take some measurements, do some calculations, put those calculations or adjustments into the printer config file, and then reprint the tuning tower to see the results. The second method, which is sort of automatic, uses the Raspberry Pi as a secondary MCU, which sends a series of signals to the stepper motors in increasing frequency, and then uses an accelerometer which is attached to the Raspberry Pi to measure those frequencies for resonance, and then spits out the results in a nice CSV format. You then use those results to calculate the best frequency along with the best shaper for that specific printer. I'll be sure to cover both methods in this video, but that's enough for me. Let's get into input shaping tuning.
Starting off with the manual method, the first thing we're going to want to do is we're going to want to download this tuning tower STL. So we'll right click, download that. Now that we have it downloaded and we have it open in Ultimaker Cura, the first thing I want to point out is to leave the object oriented the way it opens in Cura. It's going to look like it's out of place, but it is correct because we have the X actually going down the Y axis, and then we have the Y going down the X axis. That's how it's meant to be, so just leave it as such. So now let's dive into the slicer settings that we need to change in order to print this ringing tower. So first up, starting with layer height, it suggests a layer height of 0.2 to 0.25. I print at a 0.2 with a line width of 0.45. Next up, it says set the infill and top layers to 0. So we'll scroll down here. We'll set the top layers to 0. We'll also set the infill density to 0 as well. Next up, it recommends printing with 1 to 2 perimeters, but also it's better to print in spiralized vase mode. I just print with 1 to 2 perimeters. So I set my wall line count to 1, and it recommends here to use a 1 to 2 millimeter base. So what that means is for bottom layers, I set the bottom layers to 5. Next up, we'll cover speed. It says to print around 80 to 100 millimeters per second. For my tuning tower, I typically print at 100 millimeters per second. If you find that is too fast and too violent for your printer, I suggest backing that down to the 80 millimeters per second. All we're looking for is to get a clean printout so we can have precise ringing marks. Next up, we want to make sure the minimum layer time is set to 3. Typically, this isn't shown in default slicer settings. So what you have to do to possibly find this is just type in minimum here, and you'll look for it under the cooling section. And you can change this to minimum layer time. We want to make sure this is set to 3, which it already is. To get back to view all of these slicer settings, just click on the X here, and that'll show all of these slicer settings again. The next thing we want to make sure is under the speed section, we want to make sure we don't have acceleration control checked or jerk control checked. We want to have Klipper handle all of the accelerations in the tuning tower settings. We'll cover that a little bit later. Finalizing the rest of my slicer settings, you have to set the printing temperature to whatever filament you are using for the ringing tower. I am using PLA, so that means I set the printing temperature to 215 along with the bed temperature of 60. For your retraction settings, you keep these to whatever your standard retraction settings are for your printer. Next up, we don't need any support. We don't need any build plate adhesion. The spiralized outer contour is the smooth vase mode in Cura. Make sure you don't have that checked. Like I said, I just do the one wall setting. Next up, for cooling, you want to again set this to whatever the defaults are for the filament you're using. Me again using PLA is good at 100% fan speed, except for I don't have any fan speed for the initial layer, and I assume a regular fan speed at layer 4 after that. So this pretty much covers all the slicer settings. Next up, we're going to go through changing the printer CFG and also setting up Klipper to run the tuning tower. So let's hop over to Octoprint and we'll get those things set up. So now that we're over here at Octoprint, we want to make sure our ringing tower is loaded, which it is. Now, my Octoprint may look significantly different than yours. I use UI Customizer, so the layout may be different. But what you'll want to do is you'll want to hop over here to your Klipper tab, wherever it is, and then you'll want to open the printer CFG file. Now that we are in the printer CFG file, we're going to want to modify just a few settings. The first up that we're going to want to modify is over here, the max excel and the max excel to DXL. So the max excel, we want to set this to 7,000. And the max excel to DXL, you may not have this line in your printer CFG file. So all you'll have to do is right click, copy, and paste it into your printer CFG. I just have to uncomment mine. So we will set this to 7,000 as well. Not 70,000, 7,000. All right. And next up, we want to make sure square corner velocity is set to 5. Now, if this isn't in your file, you do not need to add it. By default, Klipper has square corner velocity set to 5. So after we have these lines changed and set, we'll go ahead and save our Klipper config. Once our Klipper config has been saved and it restarted Klipper, we're going to hop over here to the terminal tab. Over here in the terminal tab, I suggest suppressing your temperature readings. That way you don't get an overclutter of your terminal. The first thing we're going to want to do is over here at step 4, we're going to want to highlight set pressure advance to 0. We haven't set up pressure advance yet, but if you have it in your printer CFG file, this sets the pressure advance value back to 0. Next up, we're going to want to, if you have Input Shaper in your printer config file already, we're going to want to set that to 0 as well. So we highlight the set Input Shaper frequency X0, Y0, copy, paste that into the terminal, press enter. So if you do not have Input Shaper set up in your printer config file, or if you have it commented out, you'll get the unknown command set Input Shaper. That's completely fine as long as it's not in your printer CFG file or it's commented out. If it is in your printer CFG file and it isn't commented out, this will set the frequency values to 0 for X and 0 for Y. The next thing we're going to input is we're going to set up our tuning tower. So we highlight this line right here, which is under section 6. Right click, copy that in, and we'll paste that. Now, before we press enter here, I want to make a few changes. We're going to start the acceleration rate at 500. Now, this, again, for me, I found is a nice conservative start point for Ender3v2s, especially if they're default factory settings, because once you start getting into the higher acceleration values, it starts to become too violent for the printer to handle. And like I said, again, if we scroll down here to this picture, you'll be able to see clear, precise ringing marks. This is the main concern that we're looking for. We don't need to finish the tower. We just need to get to the point where we have clear, precise ringing marks. So again, before you hit enter, set the acceleration start equals to 500. So once you have that changed, just press enter. That'll set up Klipper for the tuning tower. So after we have Klipper set up, ready to go, we are actually ready to start our tuning tower print. So after we have the tuning tower sliced up and the Klipper settings ready to go, we're ready for our first print of the tuning tower. And so we just go ahead and start the print job. After the print job is done, we'll continue from there. So I'll see you after the print. Over here at the printer now, our tuning tower is done printing. As you can see, there are already marks on here because I went through and did this recording previously and I realized I messed a few things up. So looking at the tower, X corresponds with X. So the back side of X is our X frequency that we use, and Y, the back side of Y, corresponds with our Y frequency. Looking at my previous X marks, I try to count every ring between the first mark and the last ring, which you really don't need because looking at it closer, you can see the rings remain consistent between the first ring and the last ring. So you only need to count a few of the precise rings that you can clearly see, which I'm going to change here with a new mark. So putting in this second mark here, I'm going to move it a little bit closer to the last clear and precise ring I can see, and then I will count between those two marks and just ignore this last one. Same thing over here on Y. I'm going to move the last mark in to the last clear and precise ring, and then just count the rings between these first two marks. Looking at the notepad here, we have the equation for calculating frequency. V is the velocity you put into the slicer. N is the number of rings between the marks. And then D is the distance between those two marks. So starting with X, we'll get our N value and our D value. Making sure we have the correct side to get our X measurements, I'm going to use a set of calipers to measure the distance between the first mark and the last mark. Now this isn't going to be 100% accurate, but I'm going to try to get it as close as I can. It is quite awkward to hold a set of calipers and the ringing tower to try and get a correct measurement, but I come up with a measurement of 10.39. So we're going to write that measurement down later after we try to count the rings. Now this is where I made my second mistake. Trying to look at a ringing tower and count rings through a 3-inch LCD on the back of a camera is proved to be quite difficult. So I came up with the original amount of 3 rings, but upon further inspection here, you can see that with counting the orange marks here, there are actually 6 rings between the first mark and the last mark. I could not see the smaller, less defined rings between the larger, more defined rings while I was looking through the LCD display. But when I was editing the video, I noticed that they were there. So I'm going to add that to my calculations later on, and you'll see it at the end of this section. Moving on to measuring our frequency for Y. Again, we're just going to repeat the process here. We're going to measure the distance between the first two marks as closely and accurately as you can. Again, it's quite awkward to hold the calipers and the ringing tower, but it came up with a value 8.63. Now we are going to calculate the number of rings. This was a little easier to do and there weren't any hidden rings I missed. So it's just 3 rings between the first mark and the second mark. As you can see, for the N value for X, I changed that to 6. N value for Y was still 3. The D value for X, 10.39. The D value for Y is 8.62. Let's head back over to the computer and we'll do some calculations and change some printer configs. Back over here at the printer, our adjusted tuning tower is done, so let's have a look at it. Right off the bat, you can clearly see the ringing has been greatly reduced. It's not completely eliminated yet, but it is significantly reduced. Looking at the x-axis though, we can see these vertical lines. I attributed this to a mechanical issue. What I didn't do in a long time is actually clean the y-axis extrusion. So I had a lot of dust on there from the palm wheels, and once I clean that, I'm going to run another tuning tower to see if these vertical lines still persist. But as far as the rings go, from the ringing resonance, you can see they are greatly reduced as well. Looking at the backside here, this is where it becomes really apparent that the resonance has been reduced. X is almost a night and day difference between the top and bottom as far as a resonance goes. There is still some, you can see it at the top, especially on Y here too. It's been greatly reduced, but there is still some at the top, which is the higher acceleration values, which is honestly to be expected once you start hitting higher acceleration values. So we'll flip it over, and we will check resonance along the outsides. And again, it is greatly apparent that the ringing has been reduced between the before tuning and after tuning. Again, there's still some adjustments that can be made. We'll talk about that after we head back over to the computer. But as a first pass through manual resonance compensation tuning, I'm actually really happy with these results. So let's head back over to the computer and we can further discuss what more tuning can be done to eliminate what little resonance is left. Back over here at the computer now, we have a few options we can do if you need further tuning on your ringing tower. If not, if you're happy with the results of your ringing tower, congratulations, we can move on to the next step. But if you're not happy, like I said, for manual tuning, we have a few options on what we could do. We could change our input shaper type. Since we just ran MZV, we could change our input shaper type to EI, which is a little bit more aggressive input shaper. Another thing we could do is if your resonance is still quite significant, you can do the whole measure and count and calculate a new resonance frequency. Another option is if one of your axes is perfect and the other one is slightly off, you can actually set different input shapers for each axis. So to give you a quick demonstration, I'll head over here to the Klipper tab. We'll open up the Klipper config file. I'll scroll down to my input shaper section. This is the input shaper we set earlier in the video. But what I used to have before is I'll backspace this so it's a little bit easier to see, is when you set your input shaper frequency, you can actually set the input shaper type for each axis. So for X, I use MZV. For Y, I use EI input shaper. And they have different frequencies and different input shapers for each axis. So that's another option you can have as well. At this point, it's essentially fine-tuning the input shaper. So if you're happy with your results, like I said, congrats, you can move on. If you're not happy and there's significant ringing, I would suggest remeasuring it, doing the calculations again, and coming up with a new frequency, and then running another tower. If you are happy with one axis, but another axis is just slightly off, what you can do is just change your input shaper type to EI. Give that a try. I'm not going to go into further tuning of my input shaper. I'm just going to move on to the next section, which is automatic tuning of the input shaper using the accelerometer. It just makes life a lot easier because you don't have to mess around with trying to calculate and stuff like that. It pretty much does everything for you and spits out the answer you need. And then from there, you can fine tune it. In this section of the video, I'm going to go over how we can use the accelerometer attached to the Raspberry Pi and the printer to measure our resonance and tune our input shapers. Starting off, the accelerometer we use is an ADXL345. I'll provide a link to them where you can find them on Amazon in the description below. I'll also provide a link to this webpage in the description below as well. But essentially, we just use this little accelerometer, again, attached to the Raspberry Pi to measure our frequencies. What the Raspberry Pi does is it sends a series of signals to the printer, and whichever axis we're measuring at the time, it'll vibrate the printer in the direction of that axis in increasing frequencies, starting at 1, going up to like, I think 131, 132, somewhere around there. And that spits out what our resonance is in those frequency ranges, and then it picks the best frequency for each input shaper that's available through Klipper. So starting off, you see a picture of how it's supposed to connect to the Raspberry Pi. I'm not going to go into detail with that yet. That's going to be in the next section of how to wire it up and connect it to the Raspberry Pi. So we're going to first actually set up the Raspberry Pi so it can use the accelerometer, and also it can measure the values that we need through NumPy, and we can also get a nice little graph to spit out what our resonance graph looks like through Matplotlib. So the first thing we're going to need to do is we're going to need to open up Putty. You should have this installed already from our first section of installing Klipper onto the Ender3v2. So we're just going to open up our session of the Ender3v2. I'll drag that over here. So again, password or Pi, and then your password to log in. So now that we're in, it's essentially just a copy and paste. We're going to copy this in the NumPy install. This will take a while. It can take upwards of 20 minutes to get done. So once that's installed, I'll cut back and we'll continue on from there. So now that NumPy is done installing, we're going to install matplotlib. So the next two lines that we're going to highlight and copy over are these right here. So we just click the copy icon, right click to paste those in. It's going to ask us for a pseudo password. Now that we've entered our password, it's going to install matplotlib. This should not take as long as NumPy to install, but I'll cut back as soon as this is done and we'll continue from there. All right, so I've ran into this, and if you run into this as well, since we copied both lines, it did the sudo apt update, but it did not run the sudo apt install Python matplotlib. So we're just going to highlight this line individually after the sudo apt update runs. So we'll copy, we'll paste that in and press enter. So that runs, and that will install matplotlib. It's going to ask us if we want to continue. So we just press Y here, press enter. And then, like I said, I'll cut back once this is done. So now that matplotlib is installed, we're going to move on to setting up the Raspberry Pi as a secondary MCU to run Klipper. So we'll navigate over here to this other web page. Again, link will be in the description. And basically this allows the Klipper to be installed as a secondary MCU and gives Klipper the ability to control the GPIO pins on the board, which will have connections to between the Raspberry Pi and the accelerometer. So to scroll down here and get this started, we will copy these three lines right here. Just click the copy icon, paste those in. That'll set up Klipper. That'll run the script to install Klipper as a secondary MCU. Next, we're going to have to enable the SPI. This is in the Raspberry Pi config options. So we're going to do sudo raspi -config. This will bring up our software configuration tool. We'll go down here to 3. We'll scroll down here to SPI. We'll hit enter. Would you like to enable the SPI interface? Yes. And once that is enabled, we're going to go over here to finish. This will bring us back to the terminal. Next, we're going to have to set up and flash the MCU with Linux process. So we'll copy the cd Klipper make menu config. This will bring up the Klipper configuration tool. Again, we click on microcontroller, make sure it's selected as Linux process. What we'll do is we'll hit Q, we'll save that. If you should be prompted to save there. For some odd reason, I wasn't. I think I already did this flashing the Linux process, but I'll go through the steps again anyways. So after we set up the Klipper configuration, we're going to stop the Klipper config. We're going to stop Klipper. Once Klipper is stopped, we're going to flash the MCU with the make flash command, and then it's going to restart Klipper after that. So once we have that done, just in case, you might get a permission denied thing. So you'll take the next command, copy that, paste that in, and then we're good to go from there. So after we have the Raspberry Pi set up, ready to go, we'll go back over to the measuring resonance webpage. And then this is where we'll go back over to Octoprint to set up the printer config file. Back over here in Octoprint, navigate over to your Klipper tab, and then open up your printer config file. We're going to add a few lines to the serial connection section of our Klipper config. I already have these in, but you'll need to add them. Basically what you're going to want to do is you're just going to want to highlight this whole text box, copy it, paste it in under your original MCU section. I already have it in here, so I'm just going to uncomment it real quick. Now, everything in here remains pretty much exactly the same from the highlighted and copied section. There's one thing I want to change though, is the probe point is essentially where the printer head moves to when it does the resonance testing. So I like to have mine essentially in the middle of the print volume. So I change this to 118, 118, and then 150. So this will put pretty much the probe point at 118X, 118Y, 150Z. So it'll be pretty pretty close to the center of the build volume, and we'll get our measurement from there. Other than that, like I said, everything pretty much remains the same. So we'll save this. Once this saves, we're going to move on to our next section, which is connecting the accelerometer to a Raspberry Pi. In this section of the video, I'm going to go over everything you will need to measure Input Shaper automatically on Klipper. First up is the ADXL345 accelerometer. One thing, when you purchase the accelerometer, you want to pay attention to the pinout on it. I'll provide a link to the ones I have in the description below. Next up, we have the nozzle amount for the accelerometer. This will be used for measuring X resonance frequencies on the nozzle or the print head. I have it set up so it connects right to the ADXL345. Next up, we have the bed mount. I use an M3x20 bolt with an M3 nut, and this connects right to the build plate. You want to make sure not to tighten it too snugly because you don't want to damage the hot pad underneath, but just snug enough to where it doesn't wiggle around when you try to move it. The next thing we're going to get into is the wiring. I will go further in depth with this in a little bit, but I use a 4x2 DuPont connector. This connects to the Raspberry Pi side, and on the ADXL345 side, I use two 1x3 connectors. Again, don't worry about the pinout right now. So here's a rough drawing using my Microsoft Paint magic. I've also tried to make it colorblind friendly by changing the dashes for each of the colored wires and where they go, using numbers and letters to match them up. So on the left side, we have the 2x4 connector, which gets connected to the Raspberry Pi, and each one of the pins is labeled with the Raspberry Pi's respective GPIO pin. On the right hand side, we have the two 1x3 connectors, which are labeled with the ADXL345's respective pin labels. So starting off with the pin 1 on the Raspberry side, this is the 3-volt connector. This is the red wire or the solid line, and I connect this to the B connector on the top 1x3 pin. This is labeled VCC on the ADXL345. On the bottom, next up, we have pin 2. This is the short dashed line. This is GPIO 10 on the Raspberry Pi. This connects to the SDA pin or E on the ADXL345. Next up, GPIO 9, labeled 3. This is the really short dash line. This gets connected to D or the SDO pin. Next up is pin 4. This is GPIO 11 on the Raspberry Pi. This gets connected to F or the SCL pin on the ADXL345. Moving to the top, we go to pin 6. This is the ground or long dash line. This is the black line. Gets connected to A, which is labeled ground on the ADXL. The last wire that we are focusing on is GPIO 8 or the 8th connector on the 4x2 connector. This is the medium short dash line or the blue line. This gets connected to connector C on the 1x3 connector or CS pin on the ADXL345. So these are how I have my connectors wired up to connect the ADXL to the Raspberry Pi. I'm going to put this picture, link to this picture in the description below. That way you can pull it up when you go to wire up your connectors. So now we're going to connect the connectors to the ADXL and Raspberry Pi. First up, we're going to connect the ground VCC and CS connector. That is the top connector from the previous diagram. Next up after that, we're going to connect the SDO, SDA, and SCL connector. That's the bottom connector from the previous diagram. Next up, we're going to connect the Pi connector to the Raspberry Pi. What you're going to want to do is, having the Pi facing this way, you're going to want to count down 8 pins and connect the pi connector to the 9th pin with the 3-volt connector facing up. So the 3-volt connector is facing towards the back of the Raspberry Pi. After that, this is how both of them should look when they are connected correctly. The last thing I forgot to add to the build plate are these two M3x6 connectors. You'll need these to connect the ADXL to the bed and nozzle adapters. All right, so next up, we're going to take the ADXL and attach it to the nozzle adapter. You're going to want to take the two M3x6 bolts and securely fasten the ADXL to the adapter. You're going to want to make sure not to over tighten this because you don't want to smash or crack the PCB board of the ADXL, but you want to make sure it's snug enough to where the ADXL doesn't wobble around. After it's securely on the adapter, we're going to connect the wire connectors as mentioned in the previous section of this video. I'm not going to go over it again, but once they are connected in the right order, we're going to go ahead and home the printer. You do not want to move the printer at all while the ADXL is attached to the nozzle. This could lead to smashing the ADXL into the print bed. So after that, I'm going to raise the printer to the appropriate height, the 150 on the Z-axis, like we mentioned earlier in the printer config. So now that we have the ADXL onto the adapter, we're going to attach the adapter to the nozzle. To do this, I'm going to use an MK8 nozzle, which is the default Creality hot end nozzle. So we take the nozzle and then we pretty much just screw it into the hot end like we would a normal nozzle change. Once that is in and secure, we make sure it doesn't move around at all. And now we're going to head over to the computer to test resonance for X-axis. All right, so now that we have the accelerometer hooked up to our X-axis, we're going to make sure our accelerometer and Klipper are communicating. So what we're going to do is we're going to highlight accelerometer query. We're going to copy that and we're going to paste that into our terminal and hit send. We should be prompted with a response here. If you have values in your X, Y, and Z axis, that means all communication is good to go. So after we have that established that our accelerometer is talking with Klipper, we're going to go down here and measure our resonance. So since we have our accelerometer hooked up to our X-axis, we're going to test our resonance of the X-axis first. So we'll copy the X-axis line. We'll come over here and we will paste that into our terminal and we will hit send. Now you'll see a series of frequencies go out through the terminal and it's testing the frequency. You want to stay by to the emergency stop button just in case it gets a little too violent for your printer. I've done this before, so I know my printer can handle it well, but we'll head out and see what's going on over at the printer. After we are done testing the resonance for X, we're going to remove the adapter from the nozzle. Once we have the adapter off of the nozzle, we'll remove the two M3x6 bolts. For whatever reason, I decided to do this off camera, but take the two M3x6 bolts off of the adapter, removing the ADXL from it. Next, we're going to attach the ADXL to the Z adapter. This is the bed connector. So you take the M3x6 bolts and tighten them down to the bed connector. Next up, we're going to attach the bed connector to the bed. We're going to secure it with the M3 bolt. Again, do not over tighten this. You'll ruin the hot bed. Now we're going to head back over to the computer and test Y resonance. Over here at the computer, one more time, it's now time to test the resonance for the Y axis. So we scroll down here a little bit, copy this line in, test resonance axis Y, come over here to the terminal, paste that in, and it'll go through the same process of scrolling through frequencies and hitting each different frequency as it tests the resonance of the Y axis. Once this is done, I'll cut back and I'll show you what to do with the exported CSV files. So now that we have run test resonance on both the X and Y axis, we have our results in a nice CSV file. The question is, what do we do with that CSV file? So that's what we're going to move on to next. So the first thing we're going to want to do is we're going to want to open up PuTTY. Once we have our PuTTY session open, we're going to log in. So now that our PuTTY session is open and we're logged in, we're going to go back over to our Klipper measuring resonance page, and we're going to take these lines right here. These are scripts, and we're going to copy these scripts and paste them into PuTTY. Now what these scripts will do is it will take the results that are in our CSV file and actually convert them to a nice, easy to read image. And once these are done running, we'll take that image and we'll be able to use that image to change our printer config file to put our recommended input shaper in. So now that these scripts are done running, the next question is, where are these images? This is where we're going to have to open up WinSCP again. So now that we have WinSCP open, we're just going to have to log in. So ask for the password, type that in. So what we're going to do is we're actually going to have to navigate to the root folder. And in the root folder, we'll go down to the TMP folder. We'll open that up. And you'll be able to see these two files right here, Shaper Calibrate X, Shaper Calibrate Y. These are actually the image files that the scripts converted these CSV files into. So I'm just going to minimize this window here, and then I will take these two files and paste them to the desktop. Once these two files are pasted to the desktop, the next thing I'm going to do is I'm just going to open up Shaper Calibrate X first so we can get a look to see what we're looking at. So let me zoom in here. Now, if you look, the results are actually in a nice, easy to read graphical format instead of scrolling through. I don't even know how many lines are in the CSV file, quite honestly. I never even looked at it. But what we do is up here in the upper right hand corner of our graph, you'll actually see each input shaper that Klipper has to offer. And then down at the bottom, it actually has a recommended input shaper there. So what we do is we look at the line, it says recommended input shaper EI. So we go to EI and we see that it has a recommended frequency of 102.8 hertz at a max excel of 19,700. That seems a bit optimistic for an Ender 3, but we'll adjust it accordingly from there. So what we do with this information then is we'll pull this over here. We will pull back up our terminal, and then we will navigate over to the Klipper page. Over at the Klipper page, we'll open up the printer CFG file. We'll scroll down to our input shaper section. I'm going to get rid of this input shaper because that was from the manual tuning section. And we are going to uncomment these 4 lines right here. So once those 4 lines are uncommented, we will take our frequency for X, which is 102.8, and our input shaper for X, which is EI. And keep in mind, as you've seen, I typed in capital EI. These need to be in lowercase. If you put them in capital, they will Klipper will not recognize them and you'll throw an error. So these need to be in lowercase when you enter them. So closing this, we are going to open up our Calibrate Y. We'll drag that over here. Once our Calibrate Y is open, we're going to zoom in to see what our recommended frequency is. As you can see, it recommends input shaper of MZV, and our MZV value is 34.2 hertz. So back over here at the Klipper config file, we'll type in 34.2 hertz there, and then we will change our shaper type to MZV. Now keep in mind, you should not copy my results. Your printer is built differently. Your printer may be set up differently than mine. You may have your resonance. You may test your print head location in a different position than what I do. So it all comes down to individual. Do not copy my results. Go through this yourself and formulate results best on what you came up with. So after we have these input shaper values put in, what we'll do is we will just save this. Once this saves, what we can do to calculate our max acceleration value, like I said, in our recommended acceleration values, it was a bit optimistic for 19,700 on an Ender 3. But you never know, some well-built machines could get that high. But to calculate our max accel, you guessed it, we'll probably have to run a ringing tower again. So that's what we're going to do next. All right, so to print our last tuning tower, to figure out where our max excel is, what we're going to do is we're going to set up everything to run the tuning tower. So we're going to come over here to our Klipper config. We're going to open up the printer CFG file. Again, we're going to go through, type this to 7. We're going to turn our max excel to 7,000. We're going to turn our max excel to DXL to 7,000. We're going to make sure our square corner velocity is still 5. We will save that. Once that saves, we're going to head over to the terminal. In the terminal, what we're going to do is we're going to start here with set pressure advance to 0. So we're going to hit copy and paste that in. Now the next line, we're not going to turn off Input Shaper this time. We're actually going to run our tuning tower with Input Shaper in. So we just skip step 5. We come down here to step 6 and we highlight this, and then we'll copy and paste that into our terminal. And again, since we're going for max excel, we're not going to reduce our start excel value. We're going to leave that at 1250, and we're going to see how the printing tower turns out later on. And this is another thing, we're going to have to actively monitor it just in case the acceleration value gets too high, because the acceleration is going to be 7,000 at the end of the tuning tower. So just in case things get a little too violent, make sure you're close to your emergency stop button. But after we have this in, we're going to hit send. This will set up our tuning tower parameters. After our tuning tower parameters are set up, we'll go ahead and load our ringing tower again that has the same settings from the previous. And then we will go ahead and print this. After this is done printing, I'll cut back and we'll evaluate the results. So now that the print has finished up, that we're looking for the acceleration values, we're going to focus on the y-axis, because this is where we're actually going to find what we're looking for. So we're going to hop over here to the residence compensation page on Klipper, and we're going to focus in on this orange image. For this orange image, each one of these little arcs or steps indicate an increase of 500 millimeters per second of acceleration. So we start at 1500 millimeters per second and we finish at 7,000, increasing every 5 millimeters of a 500 millimeter per second acceleration increase. So let's zoom in here on this orange image. Taking a closer look at the orange image, what we're actually looking for is in the red box. Primarily, we're looking for the arcs to begin separating or forming a gap between the two sides of the arc. And if you take a look at the left side of the box, you'll see a small gap start to form between the two arcs, increasing the gap as we move further right along the arcs. This is an indication that the smoothing from the input shaper is beginning to get to be a little too much for our acceleration values. So now focusing in on the green box, we see that we get 4 good arcs out before we start to separate. So the first arc represents 1500 millimeters per second. The second is 2000. The third is 2500. And the fourth is 3000. This means if we set our max acceleration value to around 3000 millimeters per second, that'll give us a good starting point for our max acceleration. Now, let's hop back over to our test print and see what we get out of the test print for our max acceleration. Looking at the y-axis of the test print now, we can see that there is a gap starting to form towards the top of the tuning tower. Down to the bottom, there really is not much of a gap to speak of. There is some bulging on the arcs, so that's sort of an indication that I need to further tune either E-steps, flow rate, or something else. The vertical lines there are from the stepper motor, either the belts or the stepper motor itself. So we're going to freeze this and zoom out a little bit, and we'll take a look to see where the gap starts to form. So freezing this and focusing in again on the y-axis, we can see that there is some gap forming about midway up the arcs in the screen. I'm going to put some highlight boxes around this so we can actually take a look at what we're focusing on. So focusing in on the green box, we can count the number of arcs before the gap opens up in the red box. So we have 1, 2, 3, 4, 5, and then at the 6th arc, that is where the gap starts to open up. And from this, we can determine our max acceleration value for the y-axis. So now that we know we have 5 good arcs, before we get too much smoothing from Input Shaper, which causes a gap between the arcs, we can figure out our maximum acceleration value. So starting at 1500 with 5 arcs, that means it gives us around a 2000 increase in acceleration from 1500. So that would mean our max acceleration value is around 3500. So what we can do is we can go to our printer config file and then input 3500 as our maximum acceleration value. I'm not going to bother going through that right now. The video is getting a little too long. I'm just going to hop over, run a test print of the calibration cube, and then we will compare the two and see if there was any sort of improvement between the first cube and the cube after we've done acceleration tuning through Input Shaper. All right, so to wrap up this video before it gets any longer, we're going to take a look at the test cube that we just finished up printing. There's definitely some Z binding going on, so I'm going to have to take a look at that. I may just have to take the printer apart and rebuild it. There's definitely, you could see like 3 lines up the side. They were consistent with last week's cube too, which we'll notice later once we get to it. The corners actually look pretty good. They're quite a bit sharper than they were last week. But for the most part, it looks relatively similar to what we had last week. So I'm hoping once I, take the printer apart, adjust it, see if I can get rid of some of the Z banding, the quality will improve. But I'll probably wait till after we adjust pressure advance. The top of the cube looks really good. I have a little bit of flow I have to adjust. The bottom cube looks good as well. Now comparing the two, you can see that, both cubes together, the Z binding is pretty much similar except for down here at the bottom. The Z binding at the bottom is significantly worse on the first cube, or the second cube, I should say, one I just got done printing. So just comparing the sides again, that Z binding on the bottom is pretty bad. But the corners though, you can see especially here on the X side that the corners are definitely sharper on the tuned Input Shaper cube compared to last week's untuned cube. So continuing our inspection of the two cubes, again, they look relatively similar. There are some improvements. There's some things that have gotten worse, like the Z banding. Again, I keep repeating that, but I really don't like how that turned out. Looking at the top, they're relatively similar. Again, a little bit of flow issue with some excessive filament being deposited on the top. The bottom definitely got better. Once you adjust your Z offset, things can improve. Now this is the part that I want to focus on. Comparing the two cubes, they are relatively similar. There are some things that got better, like the corners got sharper on the Input Shaper cube, and there are some things that got worse. But if we noticed last week, we ran the cube, it was 1 hour and 25 minutes. This week's cube knocked nearly a half an hour off that time, while almost having the exact same identical print quality with some improvements. So that is the one thing tuning improves upon, is you can get the same exact quality out between two prints, but nearly a half an hour difference in timing. So we're going to take that forward into the next video where we tune pressure advance to see if we can further improve quality of the print while also reducing time even further.
Well, that concludes this video for Input Shaper tuning on the Ender3v2. I hope you found this guide informative and it helps you get those perfect prints out by further tuning your Ender3v2 with Klipper. You'll want to stay tuned for the next video where we try to further push the print quality out of the Ender3v2 by implementing and tuning pressure advance. If you have any questions or comments, please feel free to leave them in the comment section below. As always, I try to answer any and all questions I can. If I can't, I try to steer you in the right direction for the answer. If you like this content and would like to see more from me, well, you know what to do with the whole like, subscribe, whatever you want to do. If you would like to support this channel and help me grow so I can produce even more 3D printing content, I have links to do so in the description. As always, that's enough for me, and I'll see you in the next one.